Okay, we'll get started. My name is Duncan DeVore, and I know some of you out there. Good to see you guys. I work for TypeSafe, and I'm primarily responsible for the training, Akka training, and I do a little bit of engineering around one of the plugins for Akka Persistence and do some consulting work. And one of my passions has become distributed systems. Actually, before I went to work for TypeSafe, but is distributed systems and the notion of event sourcing, and really distributed persistence and distributed identity we'll talk about today. So for our discussion, I'm going to cover several different things. First, an introduction. I think it's important, especially for those that may not be fully aware of some of the things that are going on out there. To kind of cover why we consider this type of computational solution. I'm going to talk a little bit about CRUD and my personal feelings on it. I'm going to talk about event sourcing. I'm going to talk about commands and events, Akka persistence, and distribution through sharding, Akka sharding, and then I'll end up with some consistency discussions and a conclusion. So, in general, in our world, as we start to build systems nowadays, things have changed, right? The notion of just everything, primarily from the user perspective, the demands are much higher than they used to be. The notion of all kinds of different things like how many machines we build on our traditional architectures over the last 15, 20 years. If you haven't been with a company like Netflix or something like that, you're generally pushing out on a single machine and then you're putting a load balancer in front of it and maybe trying to replicate some type of relational database behind it. In today's environment, the notion of clusters are becoming very common, right? So how do we cluster? Those types of questions get asked. How can we leverage that infrastructure? Processing power has changed significantly. My laptop, I think it's 4-core, 2-core, 4-core, one of them. And so the notion of parallelization in computing is now something that's very real. And if your application is designed properly, or perhaps the toolkits that you're using allow you to do that, you can do that, whereas in the past you could not. RAM was very expensive. That's not the case anymore, right? Back in the 90s and even early 2000s, RAM was expensive. So the notion of keeping state in memory is something that is now achievable. Disk space, the same thing. Disk space was very expensive, but today disk space is cheap. You can buy a terabyte backup disk for your laptop for what, a couple $100? 10 years ago, that would have been tens of thousands of dollars. So network latency is continually improving, right? As we have fiber and all kinds of different ways to pass the network traffic back and forth. And also the cost, oops, I want to do that. The cost of networks. For a while I ran my own ISP, and I had 2 T1s running into my establishment, and the total cost was $3,500 a month, I think. So 1.5 in and up, down and up, and then the backup T1. And I have 75 meg up and down now at my house for like $100 a month or something like that. So the cost of that, this is a big one, the number of concurrent users. When I was building applications 10 years ago, 15 years ago, several thousand, tens of thousands maybe, were considered massive. I'm talking with clients today that their expectation is 30 million concurrent users. That's not going to fit on a laptop. And small data sets, right? The data is the issue, right? We want to get the data, we want to analyze it, and we want to derive something from it that's valuable. So small data sets, hundreds of millions, billions of rows in a database were considered relatively large. Nowadays, that's small, that's nothing, right? And how do you handle that kind of stuff? How do we build systems that handle it? And latency expectations. One of the pharmaceuticals I worked for, their latency expectations were, I think, 2 or 3 seconds. Now it's instantly. What do you mean? There's no latency. I never heard of such a thing. So in order to do that type of thing, I think it requires a different way of thinking than we may have traditionally thought. And I think even though more important than that is the impact that it has on business in general. And I think this is really one of the key points about the discussion is that if businesses don't embrace new technologies, if they don't embrace the way to solve problems that are on the horizon with the internet and the volume and the load and the responsive expectations, then they have this problem where somebody much smaller than them can spin up something leveraging new technology, and they now can become a competitor. One of the clients I was speaking with was talking about a particular competitor that came out of nowhere, and within a matter, I think, of a year or two, they surpassed them in their market cap, which is like inconceivable. But it's because they can produce a projection, or they can produce a response for the customer that the 800-pound gorilla can't. And so now, 10, 15 years ago, this wouldn't be possible, but because of the technologies we have before us, we can do these types of things. And I always like this as the canonical example for that, is Netflix versus Blockbuster, right? A different approach. Blockbuster was huge, and I had a good friend of mine tell me about Netflix, and I said, "You're nuts. Why would I do that? I just run down the store and get my DVD." And before I knew it, I was like, "Wow, this Blockbuster thing's kind of cool." And then online streaming and Netflix and online streaming, and all of a sudden, a multi-billion-dollar company, because they refuse to change the way that they think, now no longer exists. And when they did try to change it and kind of do a deal with HBO, it was too late, right? The momentum was already there. So it translates into a real-world reality for business owners, right? They don't go into business for fun; they want to make money. And one of the challenges is mutating your thinking from just product to product and technology, right? A big chunk of your product is now technology, whether you like it or not, even if you sell women's fashion. Because the competitor who's going to be able to get their message to the customer faster and more efficient and more reliably is going to win, right? So these aspects, I think, become very important above, our normal architecture level. And, I believe in today's world that engineers need to begin to embrace the notion of distributed computing, and that requires thinking differently than perhaps we are classically trained. And I think you need to kind of like ingrain it into the way that you think, and that has a direct impact on how you design an architecture and how you design your business domain. And that's what the whole Reactive Manifesto is all about, right? It's technology agnostic in the sense that at the top of our stack here is this notion of responsiveness. That's the customer, right? Whether it's a user, a human, or a machine, or whatever it is, you need to be responsive at all the time, right? And so there's two scenarios, load and failure, that affect responsiveness directly. So the idea is you need to be able to be resilient, which is self-healing. It's more than fault tolerance. You need to be elastic, right? So resilience, when failure occurs, I still need to respond to the customer. That's not an excuse not to respond, to have the screen hang or whatever. Elasticity, as demand increases, I need to be able to scale outwards or upwards if it's computational. And I need to be able to still have that same SLA response back to the customer. And built on top of that is, in a distributed fashion, is the notion of a message-driven architecture, because it allows that loose coupling that horizontal scaling requires. And it also allows that loose coupling that self-healing or fault tolerance requires as well. So that's kind of the stack there. And at the end of the day, the top one is what they're delivering the value to. So you're able to still be there, even in the event of these things like failure and increased load. And as I said, I think as architects, we need to embrace that line of thinking, and we'll discuss today some of the ways that I think that changes how we currently think about things. So the first thing I'll address is CRUD, create, read, update, and delete. In my humble opinion, CRUD equals pain, and this is one of my favorite slides. Because of the implied or the implications that CRUD carries, it's traditionally tied to a relational type structure, assuming ACID transaction management. And unfortunately, that's not really distributable. So as a result, it also implies a single pipe for reads and writes, which isn't necessarily wrong. It depends on the business requirements, but it encapsulates those two concepts together and makes it very difficult to optimize them. Some of the other issues that we run into is you're CRUDing against your domain model. And almost always the domain model never matches up with the projection or what the customer wants to see. More often than not, there are many aggregate views that are a composition of various members of your domain model, and so you have to create a DTO, and then you have to, call some type of query, and you may have to loop over it and do all kinds of stuff, and you're doing this in real time. That has a significant impact. For us, when we hit about the billion record limit, all those relational queries broke down, and we had to go back in and spend hours and hours re-optimizing and re-optimizing, and that window of pain was getting smaller and smaller. And all the things that come along with this type of model. Now, I'm not saying that storing current state, which is what CRUD does in a database, is a bad design pattern. It depends on your requirements. But using CRUD and single piping to solve that problem, unless your application doesn't need to scale, or you have some very, very serious, strong consistency requirement where you have to have an ACID setup, in my humble opinion, there's better ways to do it. So you can see the things there, impedance mismatch, all these things where your relational model doesn't match your OOP, your object-oriented structure, and you're going through all these different gyrations to try to make it fit. My favorite one is when you have lazy loaded collections and then you have to annotate them with a JSON flag so that when you display it in the screen, it doesn't try to load that collection. So just I think a lot of issues, right? Issues along, a lot of times you infer state, or you have to include things in your domain model that perhaps may not be important to one particular view, but are important to another view, and all these kinds of things. Under the covers, you have generally some type of compound key or a synthetic key, which is good, but those types of key structures make it difficult to shard against, if not impossible, which impedes your ability to distribute a database. So you can do CRUD in a NoSQL database, right? But at the end of the day, the key can make your thing, if it's a compound relationship, it can make the sharding of your database difficult. So the other thing about CRUD is auditing. So one of the places that I spent a lot of time at was the energy industry, and they're like security conscious and audit conscious, right? So everything had to be audited. And so in our original design, we had to implement an external tool like Hibernate and VARs or whatever. And then we had to apply that to each table we wanted to audit. And it worked pretty well, but at the end of the day, it was still extra work I had to do. And so, that's kind of an irritation. I didn't want to have to do that, but I didn't have any choice. So a lot of times, with a CRUD scenario, especially even if you're going to pump stuff out to do big data analysis, you have to do a lot of extra work, a lot of extra composition to, kind of get the data ready for some big data tool. So I was introduced to Eventsourcing and, did a lot of study on it before I adopted it. Probably 6 months, I think I spent digging into the theory and all that kind of stuff. And said, wow, this is pretty cool. And I said, this idea is different. I've never heard of anything like this. Well, actually I had, but I just didn't realize it. So Greg Young is a big fan of Eventsourcing. You might be familiar with CQRS. He kind of invented that. His point is that the majority of businesses today store this notion of current state. So you're going to create something, then you're going to update it, you're going to delete it, you're going to query it, you're going to do something like that. So at the end of the day, when you look inside your database, you have what was the last known state or current state of that domain object or that domain concept. The notion of event sourcing actually is rather old. It goes back to some of the way mainframes store data. It goes back to so high performance systems. Because they just simply cannot tolerate in-place updating, they have to basically do append only is the idea, because the number or the volume of stuff coming in is too high. And in the energy industry, we had something called SCADA systems, and that's exactly what they do. But at the point in time, I didn't realize that they were doing event sourcing until later. So the idea is not new, but it's, I think, making somewhat of a resurgence. And I think Jan and Martin's demonstration that they gave you earlier, right before this, is a perfect example of leveraging this type of thinking, this distributed identity, as I'll call it, that relies on distributed persistence. So another thing about event sourcing is that it's a natural fit for behavioral analysis. So because you're capturing everything as an event as opposed to just updating something on the fly, you can now piece together a historical analysis of something. For example, when police interrogate a suspect, if the only thing that they had was the current state of the suspect, he looks mean, they can't really do anything with that, right? I don't even know if that's circumstantial, right? But if they have a camera, right, that has viewed a temporal boundary between hour A and hour Z, they can now watch the events that occurred, and they can piece together the puzzle, and they can see what happened. And that's the kind of idea here, right? You're capturing behavior. Now, who defines the behavior? Well, the business defines the behavior. They decide what's important. And then the architect obviously has some say in it too, but at what granularity you're going to capture that behavior is really up to you. And that's something you have to think about, right? And you have to think about with your business glasses on. So it's behavioral by nature, as I said. Essentially, the way that it works is that you have this notion of a command coming in, which we'll talk about shortly, and that command in and of itself will be validated, and it can be turned into one or more events, right, from observing that command. If it's invalid, then it gets rejected. Otherwise, each one of those events will get persisted one after another in kind of like an append-only fashion. You can kind of think of it as logging. So when you want to know what the current state of something is, you derive it, right? You derive it. Now, there is all kinds of optimizations, because if you have 1 million events or 1 billion events, obviously you don't want to replay all those to derive current states, and we'll talk about that shortly. It's a simple key structure. It's generally a GUID or a UUID or something like this. Very easy to shard against. And therefore it's distributable by nature because the key structure is simple and it's append only, so it's very fast. Now you can make it slow, but that's something you have to do on purpose. So I think this pattern, it detaches the way that you store your data and how you're viewing your business domain, right? So that relationship between the data model and how the business object is supposed to look is detached, and you don't have to worry about that, right? You're going to derive the business model by replaying the events. So what is a command? Everybody knows what a command is, right? Our parents gave them to us. Do this. You ask why. You don't need to know why. But it's an authoritative order, right? By nature, you're asking a question or you're making a request, if you will. And a command is basically a behavior. Clean your room, right? change name, right? So it's that kind of construct. And if you study DDD, if you're into that, I think in many ways it leads to a more pure implementation of that type of concept. So there are requests to perform a specific action. So register client, change client locale are examples of commands. They follow a verb-noun format. They're imperative, and they're a request to mutate state. Right? Your room is dirty now. I want you to mutate the state of your room and make it clean. Right? So they transfer messages. So the idea is it's a message that's going across, not like a data transfer object, because a data transfer object has a tendency to imply some type of state, whereas a command is a request to mutate something, some piece of state. And the other thing is they can imply task-based UI or UX because of the way, depending on the granularity of your commands, kind of like the way iOS apps work. They don't require it, but there is an implication there that's fun to explore. I personally don't, but I think it's an important thing to note about them. Conceptually, they're performing a task. They can be rejected. They're capturing behavior. By their nature, they don't expose internal state. And your repository layer now becomes extremely simplified, right? Because you're simply basically appending to the end of some structure or some database table. So the other thing is a single command can yield multiple events if that's the pattern that you want. So sometimes people want to hit one submit button that represents 5 different things. So you would split your command up and validate those things, and if they validate, then you would persist those events. Otherwise, you would yield an error back. In CQRS, they have a thing called command handlers, and they essentially receive a command and validate the command. So this is in Akka Persistence is kind of how you would do a command handler, where you would receive the command, right? You would process it. The type of command I received here is register client, and then I have some type of composite validation that occurs by calling validate registration, and then I fold over the result of that, and essentially I get back either a failure or a success. If I get back a failure, I respond back to the sender. And I say, hey, sender, there was a failure. And I like non-breaking error validation, where I might validate it all and send a batch of errors back, rather than one at a time. Or if it is successful, the very first thing I'm going to do is persist. And persist is a partial function in Akka Persistence that yields the event. And inside that area is where I will side effect. So for example, if it was something like charge credit card, after I've persisted the event, I would then execute the credit card charge or whatever. I would update my internal in-memory state model as well. But I want to make sure my command persists. There's a contractual agreement with the plugins that when they receive an event, regardless of whether they're doing it synchronously or asynchronously, that they must persist to disk before they process the next command. So you're guaranteed on the ordering. So what are events? So event is a historical result of something happening. They're indicative, and they're a sign that, this has transpired, right? This thing has occurred. This mutation of state has occurred. And as such, because they're historical, they're immutable by nature. They cannot be rejected because there's something that has happened. And I'll briefly talk about something else called command sourcing, which is a little bit different, where that's not the case because there's no such thing as an event in that scenario. But in this one, they cannot be rejected. They must be processed when you're deriving current state. And they follow a noun-verb format, and that verb format is past tense. So client registered or client locale changed is an example. They're meant to be atomic by nature. But again, the business decides the atomicity of an event or a command, right? That's where the fun is. So you're going to record something that has changed. Again, it's a behavioral concept. It's immutable. The nice thing about it is it gives you an audit log that is verifiable and that you can replay against within a temporal boundary, right, and verify things. A command or an event cannot be rejected. So the canonical model for this, or example for this, is a register, an account register. So you can imagine if your bank stored data the way that a lot of us have built applications in the past where we store current state, and you had a discrepancy in your balance and you called them up and, you know, you say I have $5,000, but I say I have $10,000, and they say, well, let us check. We just checked the current state model and it says that you only have $5,000. And they say, well, you say, well, what about these 6 transactions? I'm sorry, I don't keep history, right? I mean, it's absurd, right? It's ridiculous. But yet, that's how we build a lot of systems. We don't think about that kind of stuff until someone says, hey, I want you to do X, or I want you to do Y, or I want you to audit. So in a register, it's just a series of events. That balance on the right-hand side can be kept in memory, right, as an optimization for current state. But in the database, you're just going to have the different transactions that represent debits and credits. And then to derive the current balance at any point in time from the origin, i.e. when the system bootstrapped for the first time to now, or some boundary in between, you will just replay history. And you'll be able to have a verifiable audit log that you can reconcile against at any point in time. You know, so a lot of that I just said, but you know, validation, all these different things you can do. It also leads to an interesting way to throw things over the fence to the query side or to a big data system, because now they can capture more granular stuff and they can do whatever they want with it. So what this particular concept is about distributed persistence that's fault tolerant or resilient, elastic, scalable, and very efficient. That's what its purpose is. And it gives you these abilities of replaying and so forth. So this is kind of like a picture of that example with the address book, where you have a scenario of the different transactions that come in, and you persist each one as kind of its own thing. Now, one of the things that we'll talk about in a little bit is snapshotting and different optimizations and some different twists on things, but the way Akka Persistence does that is that Akka Persistence has something called a persistent actor. And the persistent actor, by the very nature of it, implies identity. This is where it gets really interesting. Okay? Now, one of the things that I think is important to understand is that the purpose of Akka Persistence is really to support self-healing and fault tolerance. So you have some actor that for some reason has identity, and which implies that it has some amount of state that if it crashes, it has to recreate. Okay? So a simple example would be if you have, say you have a couple actors that are monitoring maybe 5 computers, okay? And they have what I would call transient state, but they still have identity. I want one actor to monitor each computer. So in the event that one of those actors crashes, when it comes back up, it has an algorithm inside of it that's going to do all these things to check the current state. I don't care about the history, I just care about the current state. But what I do care about is that actor is the same actor I have to talk to when he comes back up from crashing. And so he has an identity. So Akka Persistence provides that notion for you. It'll spin that actor back up. The way that it does that is it uses Eventsourcing, which then leads you to, wow, if I want a more complex persistent state, which would represent some type of domain object, well, it's there for me. I can do it. I determine how much persistent state I want to persist. So in the first example I gave you, it's very simple. I just want to make sure I'm speaking to the same guy. So there's some type of ID that's associated with the machine I'm monitoring. In other examples, it can be way more complex. So the thing about the persistent actor is because it's an actor, it resolves one of the problems of event sourcing is the conflict resolution of the events coming in, in that the mailbox guarantees the order of messages, and it's also thread safe unless you make it unthread safe, right? Which you have to do. But it's thread safe. And persistent actors are designed such that if you want to do command sourcing or event sourcing, you kind of can do either. When restarted, what they do is they speak to the journal and they replay the events that they've received, and then they reconstruct inside whatever the current state model is that you require for that actor. And you have the current state back. This is done in a journal. The journal is very specifically designed for this purpose. The journals themselves are driven by the community. The last time I looked, I think there was like 10 now. There's Mongo, there's Cassandra, there's Kafka, there's Apache Dynamo, there's a JDBC relational based one. There's a bunch of them out there. And you're more than welcome to jump in and add a new one if it's not covered. But it's pluggable, and it provides journaling and snapshotting, or at least it should. The last time I looked, I think there was one that didn't snapshot yet. But the idea of journaling is just capturing the events as I discussed. The idea of snapshotting is for optimization. So if your actor's processing like tons of events, the cost of restarting in the event of failure or moving that actor to a different node for load balancing can be very expensive. And so you're provided the notion of snapshotting, and that's really driven by you. You may snapshot temporarily. Every hour you're going to snapshot. You may snapshot by the number of events that are received, right? You might snapshot, you might have some indicator that, this is our predetermined load increase, right, between the hours of 3 and 5. So now instead of snapshotting every 100 messages, I want to snapshot every 10 messages, right? You can determine the boundaries of when and why you snapshot. But what happens then when the actor restarts is it'll go to the snapshot table and it'll pull the last snapshot, viable snapshot out, and then replay all the events that have transpired since that snapshot was taken. Some of the journals will allow you, if a snapshot were corrupted, they'll allow you to set the number of snapshots that you want to interrogate, before you give up and go back to the journal and replay all the events. So just some of the features of the different journals. So in an event handler, here we have our companion object inside our actor, if you're familiar with Scala, and it has this current state model in it. And it has all of this is immutable, right? Well, it has a state class, which is a case class, and it has one method on it called update. And you're going to receive an event down here. This kind of bootstraps it. This is local mutable state, the var, which is okay. It's thread safe. And you're going to process the command that comes in, and you're going to end up calling that state. And then what's going to happen is, what's going to happen is your state is then going to take the current state that it has. It's going to copy it as a case class, and then it's going to make the changes, and it's going to copy the state object, and then reset it to that. So everything's done by copy. That's a copy. And it's completely thread safe. And now you have this in-memory model of what your current state is. Then, when you replay the actor, when the actor starts back up, this is called the receive recover, and then in this receive loop, it's essentially looking for events. So the journal will give all the events, will give it a snapshot, and then the snapshots, and it will reconstitute the state, just like you did in another event. The key here is you've got to be very careful of what you do as far as side effects. Right? So again, if you go to credit card example, I would not want to side effect that here because I already did it. Right? You can side effect in here. I don't particularly like that idea. But there are some use cases where it makes sense to do it. I would do that with caution. So a lot of what I've talked about is, the essence of active persistence. But the idea is that an actor can persist in internal state, and the underlying semantics, as I mentioned, for Eventsourcing is a pendulum store, and community building snapshots, all this stuff, state recovery, and all that. Some of the guarantees that you get are point-to-point communication and at least once message delivery. And it presents this new construct to you, identity versus state, right? How do I define what that means, especially in a distributed system? And that's where now it gets a little interesting. And this is where I would talk about maybe thinking differently, right? Thinking differently. So typically when we think of a monolithic application, a lot of our domain objects are just that. Yeah, we have aggregates and they may have entities inside of them, but a company or maybe a body, I was using this example, I like this example. A body is a class that I build in Java or Scala, right? And it may have pieces to it. When I'm thinking about that from a distributed point of view, I probably wouldn't design it that way, right? I would probably design the body in pieces, a left arm, a right arm, a left leg, a right leg, a torso, and a head. And each one of those pieces would have their own identity and state, right? They would be bulkheaded. So in the event of failure, my entire application doesn't go down. If I lose my left arm, I can still do stuff. I can still type, maybe a little slower, but, right? So if you follow what I'm saying is that I have this new notion in a distributed system of something called composable identity, right? So the system, the application of all my services that are bulkheaded and distributed, when composed together, represent that big identity body. Whereas in a monolith, I probably wouldn't have done it that way. I would have just had one class that maybe had some entities underneath of it. What that allows me to do is respond in the event of failure. My application still works and is still responsive if the left arm is lost, right? The application is, I guess if I grow an extra arm or something, that would be kind of like increased load or something, but the application is still going to work in that scenario because it's bulkheaded, because it's driven on a loosely coupled architecture that's message driven and is self-healing right underneath the covers. So now what happens when I have this notion of identity, especially if it's distributed, and it becomes too big for one machine, right? The 30 million user scenario, concurrent users. And I want those users to have identity and state and memory. Well, now I have a problem, right? Because what we've talked about so far is primarily, really maybe Akka remoting at best, right? Each one of those bulkheaded scenarios. But now I want a cluster. I want to leverage multiple machines together. If it's a stateless environment, then it's not a big deal. I can use clustering and I can send messages back and forth or whatever. But once I have identity, I have a problem because I always have to talk to the same actor. So how do I do that in a clustered environment? I don't know where the actor is in the cluster. So that's what sharding is all about. What Akka cluster sharding provides is the notion of establishing a shard across the cluster for a particular identity, whatever that identity may be. So it allows me now to distribute my statefully persistent actors across nodes. And I don't know where they are, and I don't care where they are, because it gives me the semantics that when I ask it a question, it handles all that for me. Okay? So one machine's not big enough, I cluster it. I get my resilience, my elasticity, all that kind of stuff. And then with sharding, I now don't have to worry about a registry or maintaining a registry of the location of somebody because I've sharded. And we'll see what that looks like in a minute. The other interesting thing is, let's say we have this system where we have potentially 30 million concurrent users. It's unlikely that there'll be 30 million, but there could be 15, 10 million, right? And there'll be times when new users come on and log off and stuff like that. I don't want to keep that actor, that identity around in memory. It's a waste of memory. So that the notion, the theory behind it is you activate and passivate your actors. Well, cluster sharding gives you that, right? Automatically, you configure it. You can configure to activate and passivate these persistent identities based on some business rule, right? If it hasn't received a message in 5 minutes, then passivate it. It also does the automatic creation. So when a new user comes in, if it can't find that concept in the shard, then it's going to create a new one. You have to code that, but it's still, it will automatically do that for you, and it'll begin the whole Akka Persistence mechanism. And if it's passivated, it will restart it, which will replay the journals or the events in the journal, and you'll go ahead and get your current state back. What happens is a message is sent to the shard coordinator, and you essentially establish what's called a shard region, which is a whole bunch of shards right in your cluster, and you identify that, and you send a message to it. And what happens is the first time a message comes in, the shard region will consult what's called the shard coordinator. And the shard coordinator will tell the shard region on which node that actor is. And then from that point on, it doesn't have to consult the coordinator anymore, because it now knows. Unless you restart that node, right? And the message happened to come in to that exact same node. And so that's basically what I said on that slide. In this slide, this is an example where you would set up a shard, cluster sharding, and you'd start it up. And then I set up these scenarios. So client is my identity. I have a persistent actor called client. I've established a ID extractor and a shard resolver algorithm for that client. It's not like you have to do math. You just put it in there. And then all I have to do is, as long as I know the business ID of my user, right, I can send the message to the shard region, and I know that that message will go to that actor. And I know the right actor will be updated, and that will all be handled under the covers for me, and I don't have to worry about it. So consistency. And because we're running close to the time limit, I'm going to just explain a little bit of this. Consistency is the idea of, conformity, that when we both look at something, we see the same thing. Okay? In a strongly consistent system like a relational database with ACID transactions, it's still eventually consistent, but it's trivial. It's like instantaneous. And so we call that strong consistency. In a distributed system, however, that's not the case, right? Consistency is something that needs to be managed. And depending on how you design your system, will infer how you manage that consistency. With Akka Persistence, the reason that it's consistent is because there's a single actor that represents that identity, always. So every change to state that comes in will go through that pipe, and it will always be consistent. So whoever asks that actor for information will always get the same results. In distributed computing, you have this idea of something called the CAP theorem, which is consistency, availability, and partition tolerance. And the argument is, in distributed computing, you can't have all three. This has been toyed with a little bit, and the system as a composite whole distributed system, you cannot have all three, period. You can have a piece of your distributed system that you've made the decision to make strongly consistent, accepting the fact that you may affect availability. Okay, so it's not like you can't have a strongly consistent system. It's just that as a system gets distributed, you cannot make that guarantee. So you have to make some decisions. So the scenario here, for example, is, in a lot of ways, Akka Persistence falls on the consistency and the partition tolerance side, because there's a single actor that represents that identity, whereas the availability, in theory, could be compromised in that if you exceed the number of messages that you're throwing at your actor, that the journal or the plugin can handle, then you could have an availability problem. And then there's patterns to deal with that, right? You can cache, there's all kinds of things you can do to get around that, but it really depends on the use case. But clustering in general is, it's going to be available, it's going to be partition tolerant, and it's going to be eventually consistent. So, I'm going backwards. When you run into something, and that's what eventual consistency is. And eventual consistency is essentially when you receive things, you have to verify, you have to make some decision, is this accurate? And in most cases, you can do last writer wins, right? So if I receive an event and the version of the event is 3, and I check the current state of my model and its version is 4, I know something happened there and that event is no good. So I have to reject, command, I have to reject it. That will never be the case with an event, right? Because an event was persisted. If you have stronger consistency requirements, then you look at something like causal consistency where you're implementing a particular role. And essentially it's transivity, right? If A and B and C, and A yields B and B yields C, then A must yield C. So when you're across data centers, right, and you're reconciling the consistency, it's a contractual agreement that you've built into your application. But again, you don't just do this to do it, right? It depends on the requirements of the business. The business define what the requirements, the consistency requirements are, and all this kind of stuff. And finally, conflict resolution is exactly what we're talking about. This is a sample where somebody goes offline and their in-memory model, as they're changing it, becomes conflicted with reality, the person on the left who never went offline, and I have to have a mechanism to resolve that conflict. That's a reality of distributed computing. Now, some of the toolkits abstract it away for you to a certain degree, like Akka Persistence and stuff, but it's still a reality that we have to deal with. And in Akka Persistence, it's pretty simple. We do versioning generally. You can do something more complex than this, but you don't have. It's up to you. It's again your requirements. Where we check the versioning between the command and the current state, and if they're out of sync, then you get a version mismatch error. So that's just our shameless plug for our book, where we're talking about this kind of stuff, and it focuses on Akka persistence and cluster sharding and the type-safe tool stack, but the philosophy is still applicable to other technologies. So. I do have an example. I'm not going to run it. If you guys want to come see me spin up a cluster of a bunch of different scenarios on different JVMs and then crash them and show you that the application doesn't crash, I can do that. Just grab me. But other than that, that's all I got. So, questions? Yeah. Do they have a... Okay.
Yes, your mic isn't working.
Okay. You want me to? Okay, I'll just repeat it. So
I think my question was that there are 2 ways of doing it, right? Like either I could use stateless actors and then manage the persistence on my own, like in Cassandra or HBase or some kind of distributed data store.
Yep.
Or like I let a framework like Akka Persistence take care of me. I think like for majority of people though, like who have an application already, like it might be probably like easier to sort of not use Akka Persistence but manage the state on your own, but then use stateless actors on top so that they could have like some kind of messaging going on there. So like what kind of patterns have you seen there? Like have you seen like people like take out everything that they have and put persistence in and have a framework?
it depends on the use case. One thing I'm very much against is here's a pattern that you can apply to any situation and solves all your problems, because that's just absurdity. So you need to dig in and figure out what the use case is. So if I have a scenario where I need distributed identity that has persistent state, right, then this is the solution that I'll use. If I have a scenario where I have a distributed identity, but it doesn't require persistent state other than some nominal key value when I use the monitoring the machines example, then I'd probably use something like a cluster singleton, right, or something like that. So again, it depends on what the purpose is. I would not trivialize the value of capturing data behaviorally. I would not trivialize that because you can answer questions that, and I think the police example is a good scenario of that, right? If I get the guy and I just look at him, he looks mean, that doesn't mean he committed the crime. I have to have evidence. I have to have a temporal boundary that captures his behavior and shows me either through, whatever the, CSI people do. You've seen it, right? Right. So I got to have that data to make that decision. When I'm only mutating current state, I don't have that data without auditing. And so I think that's extremely important. Do I think you should just use it out of the box? You gotta dig into your business case and see if it makes sense. There are scenarios where you don't care about history at all, right? And you just care about current state. High frequency trading a lot of times, right? Optimization, it comes in so fast that, do I really need to capture every event? I just worked with a client where we drop 100 events on the floor, persistent event, drop another 100 events on the floor, persist event. After we persisted 100 events, then we snapshot. That was the optimization they used to get over their load problem. That's what the business said was okay, because when the data scientists looked at the data, that's all they needed, right? They didn't need all 100 events every single time. And that's the thing, that's what that whole, what do they call it in domain-driven design, ubiquitous language, right? That's where that whole, the architect and the business have to work together in order to determine how the system should take shape, right? Like if I want to teach my son, if I'm going to build an application to teach my son how to write a small game, I'm not going to build an Akka cluster. I'll probably whip out Python and start coding away and teach them some basics about computing, right? So the use case drives how you solve the problem. Now there are databases that are kind of building eventual consistency models into them. But again, it depends on how you store your data. If you're always doing create, read, update, and delete, all you're doing is storing 4 behaviors, create, read, update, and delete. What can you drive from that? I don't know. You might be able to drive something from it, right? But of course, the database underneath needs to be able to be distributed too. So, yep. Any other questions? Well, great. Thanks, guys, for coming.